Hello, welcome to this video about the equation for a plane. In this video, I'm going to describe how we can find an equation for a plane. So a plane is a flat surface in 3 dimensions with infinite extent in all directions. So first of all, let's think about how we can specify a plane. Similar to how we talked about we could specify a line when we were talking about an equation for a line. The first way we could specify a plane is by giving a point on the plane and a vector which is normal or perpendicular to the plane. So this word normal is another word that means the same thing as perpendicular and orthogonal. So we use those 3 terms all interchangeably. Another way we could specify a plane is we can specify 3 points that are on the plane. As long as those 3 points don't all lie on a single line, then they will specify a unique plane, so a unique flat surface that goes through all 3 of those points. So we will eventually talk about how we can find the equation for the plane in both of these cases, but for the moment, for this video, we're only going to consider the first case. So suppose we know a point on the plane and also a vector which is normal or orthogonal or perpendicular to the plane. So this is the situation. We have the plane, which is this flat surface here. We have a vector, which is normal to the plane. And then we have a point, capital A, which is in the plane. And this boldface lowercase a is the position vector of that point. So that's the vector with base at the origin and head at that point A. So every vector which is parallel to this plane is perpendicular to the normal vector n. That's what we mean by normal vector. And so if we specify another point in the plane, we'll just give it a name, say r is another point in the plane, then what that means is that the vector from A to r, which is a vector tangent to the plane, must be perpendicular to the point n. And this is the equation for a plane. In fact, this equation using the dot product that the vector from A to R dot product with the normal vector has to equal 0. And so we could be a bit more particular if we write the vector from A to R in terms of the position vectors of the point R and the point A. And so this boldface R is the position vector of R. The vector from A to R is R minus A. And then this equation, that the vector from A to R dot product with n is equal to 0 can be rewritten this way. And this is the equation for a plane. So R is a position vector for an arbitrary point in the plane, and A is one specific point in the plane, the position vector for one specific point in the plane, and then this equation gives all the possible points in the plane. We oftentimes can rewrite it as it's shown here. Let me just get rid of myself so you can see. So if we move the A dot n using the distributive law for the dot product over to the other side of the equation, then you can also write the equation in this way. The dot product of R with n equals some scalar d, where d is the dot product with of A with n. Okay. So let's continue on, and I'm going to do an example. This is actually going to be a fairly short video. I'm just going to do this one example, and we're going to return to discussing equations of the plane later on once we've introduced some more tools that we'll use for the second case. But let's look at this example. Suppose we have a given point A in the plane and this normal vector which is specified here. Now we want to find the equation for this plane. All right, and so we have a plane, the flat surface. I draw it just as a square or a rectangle, but we're thinking in perspective here, and it really extends infinitely in all these various directions. We have a point A on the plane. We have a normal vector to the plane n, which is given in the problem. Let's say the origin is down here. I have the position vector of this point A on the plane, and then any other point R on the plane. The vector from A to R is going to be perpendicular to the normal vector n. We consider the position vector of R What that means, as I described on this previous slide, is that r minus a dot product with n equals 0. Okay, and so we actually have everything, pretty much everything in this equation. We rearrange this, as I said on the previous slide. We can write this as, using the distributive law, as r dot product with n minus a dot product with n equals 0, or r dot product with n equals a dot product with n. Okay, so this is the general formula, and now let's put in the specific vectors that we have in this case. So a is given that coordinates of the point A are 1, 0, 2, and so this vector A, the position vector, the vector from the origin to the point A is 1, 0, 2. N is also given. We give it in terms of the linear combination of the basis vectors I, j, and k, but let's write it here as a column vector. It's 1, negative 1, 1. And so the right-hand side of this equation is the dot product of A with n. Let's calculate that dot product. And so we multiply the first coefficient, or first coordinate, 1 plus 0 times negative 1 plus 2 times 1. And so that's going to be 3. And then the left-hand side is just r dot n. N is a given vector, and r is the position vector of an arbitrary point in the plane. So the equation for the plane is r dot product with n, 1, negative 1, 1, equals 3. 3 is a dot n, which we just calculated. And so if you're not used to this, it may seem a little bit strange to have this type of vector equation. This is an equation involving the vector r, which is the position vector of a point in the plane. To be a bit more concrete, let's say the coordinates of a point in the plane given by r is x, y, and z. So say r is x, y, z. And so x, y, and z are the coordinates of a point in the plane. Then if we work out this dot product, we have x times 1 plus y times negative 1, so that's minus y, plus z times 1, so plus z equals 3. And so this equation maybe seems a bit more familiar, but these two equations, this one and this one, are the same equation describing all the points on this plane. So either the position vectors are of the points on the plane, or the x, y, and z coordinates of the points on the plane. Okay, so yeah, as I said, this is a short video just describing the equation for a plane, and we're going to come back to this later on in order to describe how we can write an equation for a plane when we just know 3 points on the plane. But in order to do that, we first have to introduce something else, which is called the vector product. And this is another way of multiplying vectors together, which gives another vector rather than a scalar.